In this video, we're going to look at 3D Lewis structures. Molecules do not exist in 2 dimensions, they exist in 3 dimensions. So we use wedge and dash diagrams within our Lewis structures to show atoms that are coming out at us and atoms that are going back. So if we look at CH4 as an example, the 2D Lewis structure, we would have carbon in the middle and 4 hydrogens going around it. However, this isn't the case. This isn't what methane, which is CH4, looks like in the 3D. So I can redraw this where I have 2 hydrogens in the plane, and I'm going to have 1 hydrogen sticking out at me and 1 hydrogen going back. Notice how my wedge and my dash start from the same place. So the wedge and the dash have the same starting place. The next thing is the wedge and the dash should have the same direction. So this is what I see a lot. See how this hydrogen almost looks like it's going up? That is not what we want it to look like. So this hydrogen is going down with my wedge, and I want my other one to be going down as well. So I'm going to start at the same place and make my wedge go down. So this would be the 3D structure for methane. When you're drawing these out, when we're just starting, a really good thing to do is draw the 2D Lewis structures first, and then you can get practice and you have an idea of what it's supposed to look like. So here would be the 3D structure for ammonia. The 2D structure for H2O will be this. And since we have lone pairs on the oxygen for water, the hydrogens are just going to angle down like so. Finally, CF4 is going to look almost identical to CH4, except all of our fluorines will have 6 lone pair electrons on them. But my wedge and dash is going to look very similar. I'm going to have 1 fluorine going up, 1 angled down, 1 coming out at me as a wedge, and 1 going back into the plane of the page with the dash. Now remember, all of these fluorines are going to have lone pair electrons on here as well. So I need to show them. If you are like, man, how did you even know where to angle them? You have to know the shape of these different molecules. And that's where we get our VSEPR theory. VSEPR theory is valence shell electron pair repulsion. So valence shell electron pair repulsion. And that might sound like a lot of words, and you're like, what in the world does that even mean? Well, we're talking about the valence electrons because those are the ones that are responsible for chemistry. Those are the ones that are responsible for bonding. Electrons exist in pairs and they are negatively charged, so those pairs are going to repel each other. They're going to try to get away, far away as apart as they can. So an electron domain or an electron group is going to refer to either a lone pair of electrons or a bonding pair of electrons. But it's very important when we're looking at Vesper model to figure out how many electron groups are around your central atom. Vesper theory gives us the shapes and bond angles in the 3D. And it does that by essentially getting those electron pair groups away from each other. The geometry of the atoms in a molecule is called the electron pair geometry. Now, the geometry of all electron sets, including the lone pairs, is called the molecular geometry. The molecular geometry is usually